What specific problem does the proposed method address in the realm of future event forecasting, and how does it aim to improve upon existing methodologies?
The proposed method addresses three specific challenges in future event forecasting: the noisiness and sparsity problem, the knowledge cutoff problem, and the simple reward structure problem. To improve upon existing methodologies, it introduces solutions such as utilizing hypothetical event Bayesian networks to better assign training labels, employing poorly recalled data and counterfactual events to mitigate the knowledge cutoff issue, and incorporating auxiliary reward signals to enhance reasoning capabilities. By addressing these challenges, the method aims to refine the training process for large language models, LLMs, enabling them to develop more robust search and reasoning abilities rather than relying on memorization. Additionally, it advocates for large-scale data acquisition from diverse sources, including market, public, and crawling datasets, to enhance the training dataset size and diversity, ultimately leading to improved forecasting performance. This comprehensive approach seeks to elevate LLMs closer to superforecaster-level capabilities in event forecasting.
How does the proposed method for training LLMs for event forecasting work? Provide a step-by-step illustration of the methodology, including any novel components that are introduced.
The proposed method for training LLMs for event forecasting involves a multi-step approach that addresses unique challenges in the field. First, it identifies three key difficulties: the noisiness and sparsity problem, the knowledge cutoff problem, and the simple reward structure problem. To tackle these, the methodology introduces several novel components. 1. Hypothetical event Bayesian networks. This framework models the relationships between events and their outcomes, allowing for better understanding and assignment of training labels based on probabilistic reasoning rather than memorization. 2. Utilization of poorly recalled data. The method suggests training on events that LLMs do not recall well, such as comparative outcomes, to enhance reasoning capabilities and improve generalization. 3. Counterfactual events. By incorporating counterfactual scenarios, the training encourages LLMs to engage in reasoning based on retrieved knowledge, rather than relying solely on memorized information. 4. Auxiliary reward signals. The methodology proposes using additional reward signals, such as evaluating the consistency of reasoning or answering related sub-questions, to enhance the model's learning process and mitigate overfitting. 5. Diverse data sources. Finally, the approach emphasizes the importance of large-scale data acquisition from market datasets, public datasets, and crawling datasets to ensure a rich and varied training environment, which is crucial for improving model performance in event forecasting. This comprehensive methodology aims to develop LLMs that can effectively predict future events with improved accuracy and reasoning capabilities.
Can you provide a simple example that demonstrates the inner workings of your proposed algorithm? Walk through the main steps of the algorithm with this example.
To illustrate the proposed algorithm for event forecasting, consider the example of predicting whether SpaceX will successfully launch and return a spacecraft from Earth orbit by June 2024. The algorithm follows these main steps. 1. Label assignment. Initially, we determine the training label for this prediction. The outcome, success or failure, will be known after the event resolves, but we can also use market predictions as a label. For instance, if market predictions indicate a 70% chance of success, this value can serve as our initial label. 2. Hypothetical event Bayesian network. We construct a Bayesian network to model the probabilities involved. For example, we define probabilities for intermediate events, such as the success of initial tests leading up to the launch. This helps in estimating the hidden probability of success at the question date. 3. Training with noisy data. Given the inherent uncertainty in event forecasting, we train the model using both the market predictions and the actual outcomes once they are available. This dual approach helps the model learn from noisy data while refining its reasoning capabilities. 4. Reinforcement learning. We implement reinforcement learning where the model receives rewards based on its predictions' accuracy compared to the actual outcomes. For instance, if the model predicts a 75% chance of success and the event resolves positively, it receives a reward based on the negative Breyer score, encouraging it to improve its future predictions. 5. Evaluation and adjustment. Finally, we evaluate the model's performance using dynamic benchmarks, adjusting the training process based on its ability to generalize across similar events. If the model consistently underperforms, we may introduce auxiliary rewards or additional sub-questions to enhance its reasoning capabilities. This structured approach allows the algorithm to effectively learn from both historical data and real-time market predictions, ultimately improving its forecasting accuracy.
What specific performance metrics or benchmarks were utilized to validate the efficacy of the proposed method? How do these metrics support the conclusions drawn from your results?
The paper utilized several performance metrics to validate the efficacy of the proposed methods in event forecasting, including the Breyer score, logarithm score, and expected calibration error, ECE. The Breyer score, defined as FO squared, measures the accuracy of probabilistic forecasts, with lower scores indicating better performance. For instance, recent models like GPT-4o achieved a Breyer score of 0.133, demonstrating significant improvement towards superforecaster-level performance. The logarithm score assesses the model's sensitivity to extreme errors in probability estimates, while ECE evaluates how well the predicted probabilities align with actual outcomes, providing insights into the model's reliability. These metrics collectively support the conclusions drawn by illustrating that advancements in model training and data acquisition have led to measurable improvements in forecasting accuracy, thereby reinforcing the argument for large-scale training of LLMs to achieve superforecaster-level capabilities. Additionally, the paper highlights the correlation between improved Breyer scores and advancements in LLM performance, further substantiating the effectiveness of the proposed methodologies.
What significant results were achieved through the implementation of your proposed method? Can you describe any improvements in comparison to existing models or methods?
The proposed method for large-scale training of event forecasting LLMs has shown significant improvements in performance compared to existing models. Notably, recent high-performance models like GPT-4o and CLAUDE-3.5 Sonnet achieved Breyer scores of 0.133 and 0.122, respectively, which are closer to the superforecaster-level Breyer score of 0.096, indicating a narrowing performance gap. Additionally, the implementation of reinforcement learning with verifiable rewards, RLVR, has demonstrated that models can improve their Breyer scores, with the R1 to 14b model reaching a score of 0.197 through training on polymarket datasets. Furthermore, the integration of diverse data sources, including market, public, and crawling datasets, has the potential to expand training instances from 10,000 to over 100,000, enhancing the model's generalization capabilities. Overall, these advancements suggest that the proposed methodologies are effectively addressing the unique challenges of event forecasting, leading to improved predictive accuracy and robustness in LLMs.
In your paper, you identify several limitations of the proposed method. What are these limitations, and how do you suggest addressing them in future research?
In the paper, we identify three primary limitations in the proposed method for event forecasting with LLMs: the noisiness and sparsity problem, the knowledge cutoff problem, and the simple reward structure problem. The noisiness and sparsity problem arises from the inherent uncertainty in event outcomes and the infrequency of similar events, making it difficult for models to learn effectively. To address this, we propose utilizing hypothetical event Bayesian networks to better model these uncertainties and develop appropriate reward signals. The knowledge cutoff problem limits the training data available, as LLMs may rely on internal knowledge rather than engaging in reasoning. We suggest using poorly recalled events and training on counterfactual scenarios to enhance reasoning capabilities. Lastly, the simple reward structure problem allows models to achieve rewards without proper reasoning, which we propose to mitigate by incorporating auxiliary labels and sub-questions that encourage deeper reasoning and consistency in predictions.